Hello. In this episode, we'll learn about what is Hebbian learning and introduction to our recursive PCA. So let's see what that is. Okay. So here's the situation. We live in a world with big data, isn't it? And so what happens when there are many features, like P is a whole lot larger than one, let's say 10,000, 100,000, or million. The PCA, or eigenvectors, which were developed a long time ago, they didn't think about this big situation. And what they do is that they have a matrix, as you've seen, and they require the inverse, computing the inverse of a matrix, isn't it? It just so happens that the inverse of a matrix, if you have P features, then you need P square multiplications. Okay? So if P is 10, then 100 multiplications. That's not a big deal. But since we have big data, like Facebook, and there are many variables you can come up with, Twitter, Facebook, and all this kind of alternative data, eventually, which will be used to predict, let's say, stock prices, stock returns, and all the other things, isn't it? So what happens if P is, let's say, 1 million? Then we need 1 million square multiplication. That's kind of a lot, isn't it? So that's where the motivation of this lecture comes up. Is there an alternative? See, the problem here is that if you have, let's say, 1 million features, the traditional method tries to compute and get the eigenvectors in one shot. And that's why they at once require this a lot of explosive number of computations. But if we just need, let's say for PCA, we just need one or two, the first and second, let's say, principal components, why not compute the factors one at a time? Can we do this? And the answer is yes. There is a technique called recursive PCA, okay? And that avoids the computational burden because it does not attempt to compute every eigenvectors or principal components. It just computes one at a time. And this whole story started with a Canadian psychologist, Donald Hebb. He thought about how biological neurons work. And this is, let's spend 2 slides here. So first, how does the learning happens in our brain? Just a quick crash course on that. It's called synaptic transmission. And what it is that let's suppose that here's our fingertip, and then there's a nerve, and then it gets to another nerve, and then it gets to our brain, or something like that. I mean, of course, in reality, there are many neurons. But the point is that here, this joint is actually of interest. So here, what happens is that if the signal that's coming in here is large enough, so remember the activation function is like a step function. Only if it passes a threshold, an electric pulse will be sent here. And if that pulse is large enough, it will release some chemicals called neurotransmitters, see here. And they're stored here at the end here somewhere. But if the electric signal is large enough, it pushes out here and pops. And these neurotransmitters, which are usually like calcium or these kind of stuff, will be here in between this gap here, between the earlier neuron and the later neuron. And then and some of it, of course, will go into these holes here and then go here, right? So if many of them are coming here enough, then that stimulus is strong enough, then an electric pulse will be generated and shoots down the road here again. So the transmission here is actually the mechanism, in the sense that what we think that learning or memorizing is that if there's a signal, when would our brain remember something, is that when you get a signal, it has to transmit a signal from here and then jump here and go here. And learning means that it's easier with a lower kind of threshold, or the transmission gets easier, meaning either the holes get bigger or something like that. So it makes it a bit more facilitated, so the electric signal can be transferred easier. Is what we think that it's learning. When it's not learned, then the holes are very tiny or something, and it's difficult to transmit the electric signal from here to here. But when you learn something over time, then it gets used to it, and the chemicals gets transmitted easier from this earlier joint to the after joint. So it's called presynaptic terminal and it's a postsynaptic terminal. And here's an actual picture for it. Okay, so how do we actually learn? So that's how the signal is transmitted, and learning means that it gets easier to transmit here in the junction. The thing is that physically this junction changes in a way that it can easily accept chemicals. That's what learning does, and it's called synaptic plasticity. Plasticity means it's kind of a permanent change. In that, and Donald Hebb came here into the picture that he long time ago conjectured that neurons fired together will wire together, meaning that if you get the stimulus frequent and often enough, you will learn that the signal is there, isn't it? And here is a picture from a particular neuron from overlearning. You can see that there was nothing in here before the learning, but afterwards some branches increased, isn't it? It's that it increased the number of receptors or increased the contact area and things like this. So this kind of thing is actually really happening here. Right? So now actually with modern science, we are able to see it. So can we apply it into our AI kind of idea in the computation in computer programming? And the answer is yes. So people afterwards attempted to model it. And that's what we call Hebbian learning. But let me first show you here. There's what we call associated learning, like how smell and vision of a barbecue gets be associated and learn to, if one or the other, like the grilling side or the smell, if you see them, you can remember in your head the other one too. Let's see how that works out. So here is a situation. So there are like about 10 neurons. 10 neurons here, it goes to the next junction here. It just so happens that the weights are here in 1, 3, 5 are kind of fairly well learned. The other ones are not learned, okay? And let's suppose that the 1, 3, 5, neuron 1, 3, 5 does the smell contact, get the signal from smell, and 8, 9, 10 gets the signal from the sight, okay? And let's suppose that the threshold here, meaning if the weighted sum of the signals exceed 1.5, then a neuron will fire to the next neuron, okay? And also, let's say, the super unsupervised learning that neurons fired together idea that if they jointly get if the neuron is activated and it's here, the signal was coming in, then the weight will increase for those junctions by 0.1, let's say, okay? Let's see. So first, let's say if the order Q just comes in, 1, 3, 5 here, the 1, 3, 5 comes in, and this has already weight of 1. So it adds up to be 3, which is over 1.5. A neuron will fire. However, if you just see the barbecue here side without smell, then 8, 9, 10 gets activated and there are no weights, so it's 0, so it's not activated. Okay? But what if it learned both Qs? So 1, 3, 5 and 8, 9, 10 comes in here. And after one round of learning, so it's activated, of course, the sum here is, it sees 1.5, so it's activated. But once it's activated, it will increase those neuron synapses weights by 0.1. So here it increased to 0.1, it's 1.1. So let's repeat this like 6 times, okay? So now what happens is that, so with both Qs coming in, if we repeat it 6 times, now only if 8, 9, 10, the visual side of the stimulus comes in, there are weights of 0.6 now, isn't it, after 6 learning. Adding them up actually will exceed the threshold and it's activated. What I'm trying to say is that the smell and the sight have been associated, isn't it? And this is sort of an example of how plasticity works out. So let's see how this mathematically works out. So neurons fire together, wire together. So here is our new weight at n+1 round, and here's our old weight. So onto our old weight with some learning rate, some small number. If the y which is here, the output. So this is the postsynaptic neuron. And here are the inputs, like let's say a couple of them comes in with some weight. Okay? If the postsynaptic neuron and the input neuron, let's say Xi, X1 here, for example, if that's both fired, so then they're both one, let's say, okay, then we will add on to it to the old weight and update it, isn't it? All right, so this is basically the idea. The post and pre neurons both firing, then change the weight for that junction, just like the synaptic learning plasticity, isn't it? Except that we want the weight mathematically between 0 and 1 is probably ideal. So we add all these terms for all junctions from I = 1 to, let's say, m junctions. Okay? So technically square and then square root them. But so summing up to 1 so that it sums up to 1. So, and this is sort of like a square root of something is an ugly term. So people do mathematically approximations. If you're curious, Taylor expansion is what they do. You don't need to know. So it ends up being just expressed in this term. So this denominator can be expressed as the eta times and this here, y squared, and then omega, the weight, isn't it? And there are some small terms that are very tiny, so you can just ignore. At the end of the day, the new weight is old weight plus learning rate plus this term and minus learning rate times this term. We can group them together. Eta y is common, eta and y is common. So you get here x, and then you get a minus y omega, minus y omega. So this is called the mathematical formula for Hebbian learning. Okay? And it's called Oja rule by Erkki Oja at Helsinki. In Finland. So he developed this idea. He in fact proved that, that this formula, according to this formula, if you do this weight updating over and over again, eventually this omega, the weight will point to the eigenvector, the largest eigenvector. Okay? And I can show you the result here. So if you sprinkle out random data here, random data points, and you initially had a weight here, okay, so just have one neuron here, okay? And eventually, if you simulate, and I'll show you in a minute how you do it, eventually this omega or the W will basically point here, where the cloud, you can see the largest variation direction is here. It will actually point to this cloud. Okay? And you can also try it with other things, not just random number, but in two-dimensional IBM stock versus the market risk premium. Okay, so Standard & Poor's return minus the treasury bill. Something like that. So here's a cloud of that, and the principal component direction is here. Initially, let's start from here, where it will end up being if you simulate. We'll just approach to this. Okay? You can even do it with more, of course, like a Procter & Gamble, IBM, and market premium, and do it in 3 dimensions. You can do more stuff like in 10 dimensions, 100 dimensions. It's just difficult to visualize, but these kind of things are possible. Let me just quickly show you how it's being done. On Python. So okay, so let's import the libraries. We'll just use NumPy, Panda, Matplotlib, and Seaborn, just the standard things we use. Okay? And for the 2D random example, random numbers, let's just generate the random numbers. Let's have a starting array of, where was that? Here, okay? 0.1 and 0.4, so X and Y coordinate, okay? And we'll keep in W trajectory, the trajectories. We'll accumulate the W's over time so we can plot them. Here's a rotation matrix. I'm gonna generate a cloud with a random number, 0.05 variance, the initial condition. So this is basically these two are and rotation matrix to multiply it to here, this cloud, this random number. Basically, I'm going to get a cloud that is tilted. Okay? It's tilted. So that is basically generating the current cloud here. Okay? The random normal number of mu 0, sigma 1, but I'm multiplying by 0.05. So the sigma is, the standard deviation is 0.05. And I am rotating that in that cloud. So let's see how the training works. It's actually very simple. the presynaptic, I'm just picking up one data from the R3. The R3 are, by the way, there are many thousands of X and Y coordinates of this, basically this cloud. Okay. So get one of the dots, okay? And so that is the signal from the presynaptic neuron. Okay? And then I'm going to multiply that with the weight, so the synaptic weight, okay? And get the post synaptic neuron. So meaning, yeah, the weight times the input times weight will be the output when we have only one neuron. So times output is the post. Okay. So what's the Hebbian learning formula? The old weight plus learning range times output, and then X minus output times weight. Okay. I'm just typing that in, post pre minus post times weight. Okay. And that is my updated weight here. And I keep updating and accumulating that so I can plot the trajectory. Oh, it's already done. The original cloud, of course, we generated this here. Our initial W direction is from the 0, 0. It's here. And the W trajectory keeps track of all the trajectories that we computed, isn't it? So how that looks like is it starts from here, and the W keeps changing and changing and changing and ending here, which is lining up with the direction here, isn't it? If you plot from 0, 0, the vector points here. Amazing, isn't it? Can do it also with the stock return data. I just happened to download the stock, Yahoo Finance. So here's the date, here's the IBM stock, Procter & Gamble stock, and the market premium small minus book, HML, and the risk-free rate. Okay. I'm not going to use all of them. You're welcome to, but let me just upload the data here for the stock returns. So I'm going to just delete many of them. Let's first read in the data. So you have date, IBM, P&G, market, premium, SMB, HML factors, and RF risk-free rate. I'm going to drop the date, P&G, SMB, HML, RF, and just keep the IBM and market return. Just let's focus on these two variables. I have to demean it for principal component to work the best. So it's here. And let me just convert to NumPy and transpose it. So my initial vector, let's start from 0.1, position. And the trajectory will keep track of accumulate the weights. So if you're curious, it looks like here the data. So I'm going to copy that Hebbian learning component here. It's still the same. So I tried all the data points. It's already done. And let's scatter plot here. So our initial vector is here. The cloud is here. The direction is here. And the trajectory is basically, well, approaching to the cloud here, the direction principal component of the cloud. Pretty awesome, isn't it? But the point is that you can, the Hebbian learning or the recursive PCA method allows you to, using the data, just to compute the first principal component, and you don't have to compute all the components, especially if you have like 1,000, 10,000 factors or something like that. But also, this method, this OJ rule, has been extended to, of course, to compute the second, third, and fourth largest principal component, and so forth. In this example, I just showed the first one, but you can also, there are methods to compute the rest of them. But the idea is pretty similar, that neurons are wired together. The synaptic plasticity idea is basically being adopted. So, thank you for watching this video.